Good morning, everyone. Please have a seat. Welcome to join this session, the design, modeling, and control of high power converters. So in this session, we're gonna have 5 talks for each speaker. There will be 20 minutes presentation, followed by 5 minutes Q&A. Our first presentation is from Jayesh Motwani. So Jayesh received an integrated dual degree from IIT India in 2020. He is currently working toward his PhD, focusing on control of modular converters and a large power electronic system. Jayesh.
Excellent. Thank you. Hello, everyone. I'm Jayesh. I'm currently a third-year PhD student here at CPES, advised by Dr. Dong Dong and Dr. Dushan Borovich. Today, I'm excited to share with you our work on modular multi-level converters. In particular, this presentation will focus on control, switching cycle control particularly, which is developed within CPES. This work was supported by ARPA-E, and we are thankful for their support. All right, so over the course of this presentation, I'll firstly introduce multi-level converters. We'll then look at why we need additional control schemes when we already have plenty of these. We'll then look at switching cycle control, which is one control in particular, focusing then on closed loop capacitor voltage balancing within SCC. We'll demonstrate the experimental prototype on experimental results on our 24 kV prototype and some concluding remarks. So medium voltage converters have been extensively discussed over the past 2 days. I would not bore you with it, but what I would like to particularly discuss is the multi-level converters. And multi-level converters form an integral part of these medium voltage conversion or converter domains. And the idea here is that you can use some kind of intelligent placement of switches or submodules or cells, and you can stack them up in series to create higher voltage, and that allows you to circumvent the device rating limitations. Moreover, since multi-level converters produce a pseudo-sinusoid or staircase AC voltage, you drastically reduce your AC filter sizes. There are quite a few multi-level converters. These are all popular. These are all well commercialized. Cascaded edge bridge, however, requires individual cells, which might be expensive. Neutral point clamp and flying cap are used extensively in industry, but again, scalability is an issue when you reach higher and higher voltages. Moreover, recently, there's a new domain called modular multi-level converters, where the idea is to use small building blocks. We call them PEBB, and in this case, a half-bridge PEBB, and we'll stack them up together. And the idea here is that if you have many of these, you can reduce the voltage on each individual cell. And this then in essence translates into lower capacitor voltage and lower device voltage stress. Moreover, since we are moving towards more and more wide bandgap devices, our idea was, can we improve MMCs altogether? As I mentioned, modular multi-level converters, as the name suggests, are modular, developed by connecting PEBBs, and PEBBs you can consider as Lego blocks. So you just stack them up in series to create higher voltage. You can also put them in parallel to create higher current, and so on and so forth. And while MMCs are very good, used extensively for HVDC today, they are not as much power dense as we would like them to be. And this is a challenge CPES took about 10 years ago or more than that. And the idea here was, can we make MMCs more power dense? But before making them power dense, let's understand why they are not power dense in the first place. So MMCs, as I mentioned, have these big capacitors. Now these PEBB capacitors in conventional applications are balanced at line frequency or some integral multiple of line frequency. And what this forces the converter to do is to store charge on capacitors for a longer time period, which then results in bigger capacitors. So here I'm comparing a commercial PEBB where the capacitor occupies about 50 to 60% of the cell volume or PEBB volume. Compare that to the PEBB developed by CPES, where it's about 5 to 10%. So how do we do that? How do we go from 50% of the capacitor to 5%? Well, we have two good control schemes to do that. And I'll highlight both of these, but then I'll discuss one of these more extensively. So I'm comparing this to conventional MMC control, which is more of an average mode control of MMC. And we would compare the switching cycle control and the integrated capacitor balancing transistor approach, or ICBT control. And the idea here is that, as I mentioned, conventional control do balance the capacitors over a line cycle or something on those lines, whereas switching cycle control and ICBT control both can balance your capacitors within a switching period. So say from 60 hertz moving down to say few kilohertz, tens of kilohertz. And this allows us, because you're balancing the capacitors faster, you don't have to store the charge for a longer time period. You can make the PEBB capacitors fairly small. Additionally, you also decrease the inductor size, and ICBT even does not need an arm inductor. Conventional control as well as switching cycle control both can generate your multi-level output, which then allows you to create smaller AC filters, whereas ICBT is limited to a 2-level converter and requires fairly large filters at the AC side. In terms of scalability, SCC is quite challenging, and we'll discuss or we'll resolve these challenges today, but it still remains a question. Both SCC and ICBT have fairly high EMI emissions, and that's something we are working about, but this presentation will not cover it. Moreover, and this is a very big advantage, since we have decoupled the line frequency operation from MMC itself by balancing within a switching period, what we are allowed to do is to regulate DC-DC operation, MVDC, multi-terminal DC, using SCC and ICBT, whereas for conventional control, it's fairly difficult job. And now let's look at SCC itself and how we can use it, or what it really means. Before I go deep into SCC, I'll just highlight how an MMC looks like, or what an MMC is. So you have a voltage source, in this case, can be DC source or something. And then MMC is divided, this is one phase leg, and it's divided into two sections, the upper arm and the lower arm. Both arms have an arm inductor and comprises of some number of PEBBs or building blocks. In our case, we are looking at one PEBB per arm, for example, then we'll later scale it up. The PEBB itself is constructed by, as you can see, two switches, in this case, half-bridge PEBB and a capacitor. And then you can either insert this cell or insert this capacitor or bypass this capacitor, depending on your switching. As I mentioned, the voltage across capacitor or PEBB capacitor is balanced around VDC over N, where N is the number of submodules. In our case, N is 1, and that comes out to be VDC. And we choose very small arm inductors for SCC operation. Now, conventionally, there are two operation modes very well understood, utilized. These are you insert few number of PEBBs in the arm and you bypass the other, or say, let me rephrase it. You insert a few capacitors in the phase leg and bypass other few and generate a AC voltage at the node. These two states are, or for one PEBB per arm, these two states are very well understood. You insert the bottom arm, bypass the other, and the other way around. And these help you regulate the terminal voltage or the AC voltage. These are utilized well by many control schemes, and I will not focus more. But SCC is unique in a sense that it uses two additional states which are not well utilized by other control schemes. These are high di by dt states. So the idea here is that if you can bypass the two capacitors, or just say consider this bypassed, you can create a very high current in either direction. So in this case, if you bypass both of them, you create a higher di by dt, and which allows you to change IU, IL, and ICIR, or circulating current. Whereas you also have a state 4 where you insert both capacitors and you create a circulating current in negative direction. And these two states are very useful for SCC and will be utilized. These are also unique to SCC. So now let's look at the terminal voltage of SCC itself. As I mentioned, this is usually controlled by conventional states. So you use conventional states to regulate the output voltage, and the converter spends most of its time within these conventional states. So assuming you have very small arm inductors and you insert one capacitor at the bottom arm, you can find that the output voltage will be fairly close to Vout or VDC, because considering this as a ground. Again, this is different, slightly different from conventional MMC. Compare that to state 2, where you bypass the lower arm and you have small arm inductor, so not a large, and low di by dt in these states, conventional states, and your output is 0 or close to 0. If your converter spends D and 1 minus D in each state, your output voltage would be somewhere close to D times VDC, and that's how you regulate the output voltage for one PEBB. Moreover, as I mentioned, there are two high di by dt states which have much lower duration. These are more of a transition states, and it will become much more clear in the next slide. And these high di by dt states actually control your arm current, because you control di by dt, you control current transition from one value to other. And you'll realize that arm current is the only thing going to the capacitors themselves. So as long as you control the arm current and regulate it well enough, you control the capacitor voltage. So in a sense, you can use these high di by dt states to regulate the capacitor voltages themselves. All right, it's still a lot of theory. How do we actually do that? So as I mentioned, converter spends most time in states 1 and 2. Let's look at state 1 first and real implementation. So you have KCL, where you have upper minus lower equal to load current, fairly simple. And what we are trying to do is we are trying to maintain the net PEBB capacitor voltage deviation over a switching period, which is in our case 100 microseconds, to be 0. Well, whenever the capacitor is inserted, you can regulate the current through it to be 0. Well, easy enough, easy said. You can make IL equal to 0 and the upper arm takes up the rest of the load current. Similarly, for the state 2, it's repeating the same process. So upper arm is inserted. You make the current through it 0 and the lower arm takes up the rest of the current. And this is fairly well understood. This is not a new thing. But conventional controls cannot do that because they firstly do not use the high di by dt states. Moreover, they have big arm inductors, so they cannot change this current very fast. SCC has smaller arm inductors, and we essentially use this high di by dt states, which then allows us to change arm current very fast, or arm current itself switches from one value to another. So 0 to minus I load and I load to 0. If I look at the operating waveforms, you have the gating signal. So gating signal for upper arm, gating signal for lower arm, and there's slight delay, which introduces this high di by dt states and interleave between the normal operating state, conventional states. And because you have these high di by dt states, you can control the current from one value to another very fast. So when SU is inserted, you pass 0 current through it. And when SL is inserted, you pass 0 current through it most of the time. Again, these are simplified waveforms. So there's a second order equation going back on the back. These are not all linear, but we'll fix that later. And arm current themselves are controlled using peak current mode. So as soon as current hits this value, it turns off. And similarly, as current goes down, hits the value, turns off. That provides us very fast control. And then we can maintain the PEBB capacitor voltage deviation to be 0. At the output side, we have similar nodal voltage, just like conventional MMC. Now, of course, MMCs are not used for one PEBB per arm. It's generally multiple PEBBs per arm. So PEBB voltage in our case or in our application was limited to 6 kV insulation. But if I want to go to higher voltage, which was 24 kV our operation, we need 4 6 kV PEBBs together in one arm. We can easily put that. Putting them is not difficult. Controlling them is. So we have this gating signal on there for each PEBB. And the idea here for distribution within the PEBB itself is that PEBB within the same arm, we would like to maintain even loss distribution, and then we maintain the same insertion or duty ratio. So here, for example, I'm showing the PEBB, one PEBB per arm gating, which we showed in the last slide. And if I have to scale it up for 4, I can just interleave them. And this is for D less than 0.25. For others, we have solved it, but I'm not showing this in this presentation. So again, the idea here is that you have one gating signal, you break it into 4. Of course, the time period remains similar or same, and you interleave them. So now I'll quickly go over the comparison from 1 PEBB to 4 PEBBs. So you interleave. Again, nothing changed. We are just interleaving the signal. We were delaying 1 gate signal. Now we are delaying 4 gate signals. And if you have n PEBBs, you are delaying n gate signals. the arm current was changing twice. Now we are changing it multiple times, again, 2 times n. And then we are able to maintain the capacitor voltage to deviation to 0 in 1 PEB. We are able to do the same for 4 PEB for arm. So again, the fundamental idea is same. You have these high di by dt states that allow you to control the capacitor voltage. But again, the arm current design here, or the current design here, is slightly different. So I'll briefly cover it, but we can discuss this later. The idea here is that you have, let's look at cell L1, for instance, which is inserted for a very short time period. We learned from our previous discussion that if something is inserted for short time period and we would like to maintain its deviation to 0, well, we maintain current through it to 0. So IL2 turns out to be 0. Similar process can be repeated for the other 3 cells in the same arm. But now what we have done is you have, in effort to maintain the capacitor voltage deviation at the lower arm, you have compromised the upper arm. So upper arm is now more charged than it needs to because it's inserted for 3 times where arm current is positive. Well, no worries, we have 4 more states and we can use them to discharge this upper cells. So we have these 4 other states where we discharge this cell. Arm current design can be mathematically defined. I will not cover it, but it's fairly simple. Now, while this is easy to do, in practical application, we tried this. So you have this reference generation, you have duty ratio, you know your load currents. You can create a pattern and you can feed it to peak current mode control and it can feed to MMC, works good, right? Well, not so much, because in real life, you have errors, delays, communication, dead time, anything can go wrong. Well, to demonstrate this idea, we operated it at 7.5 kV and each PEB is maintained at 2.5 kV. And if we don't have any closed loop balancing control, the capacitors themselves do deviate a lot because it's very fast control and the PEB capacitors are chosen very small. To fix this, we developed a closed loop control scheme where the idea is that we take the PEB capacitor voltage measurement in real time, compare it with a reference, change our arm current pattern and duty ratio in the central controller or outside system and plug it into the system. And this allows us to balance the capacitor voltages very well. Let's look at it in action. So as I was saying, we have control over arm currents and duty ratio. In conventional MMC, you usually have control over duty ratio more or less. So you have, and here I'm considering one example where you have a lower arm cell L1, which is inserted for a short time period. We developed this current pattern in the previous slide. And the idea here is if we see L1 or this L1 is less charged than it needs to be, what can we do? How can we bring it back to its reference value? Well, it's fairly simple. It's only inserted for one time period. We don't have anything else to do than to increase the current through it, to charge it more. And we can easily do that. So whenever the VCL1 is inserted, or whenever the capacitor across VCL1 is connected, we pass more current through it. And that allows us to balance the capacitor, bring the capacitor voltage back to its reference value. Similarly, you can change the duty ratio assignment or insertion time between the cells of the same arm. So you have cell U1 here, which is inserted for a fairly large time, and we saw how to maintain the current across this. And say in one instance, it's more charged than it needs to be. Well, again, what else can you do? You need to bring the charge down. You decrease the time it's being charged for, increase the bypass time. So whenever it's being charged, in this case, IU4 was charging this capacitor, you decrease the time it's charging it for. In this case, decrease the IU4 by delta T and increase the bypass time where it's not doing anything. That allows us to, again, balance the capacitor across VCU1. Now I'll demonstrate this idea. So we plugged all this into our control systems, maintained a very fast communication network, and we demonstrated it on our 24 kV prototype. So we are operating it as a pump back where two phase operate in phase opposition mode. The idea here is, and this is the common method testing for medium voltage converters. And the idea here is that you will have one phase pumping in a positive current and the other phase taking in this negative current. And overall, then the source only provides the load of the system, and the power circulates in between these two phases. For our system, our DC voltage was 24 kV, and PEBB voltage itself was 6 kV. You'll see that the PEBB capacitor here is 32.5 microfarad, which is much smaller for a 2 megawatt converter. Of course, we'll have quantitative comparison in our papers. Now, looking at its operating waveforms, and what you're seeing here is the current across the two phases. So in the top is the current across phase A, in the bottom is the current across phase B. So I load here, it relates to this I load here 25 amps, and it's supposed to be DC-DC. So your I load is 25 ampere DC. Your upper arm current here is the same upper arm current, as well as the lower arm current is this lower arm current. And you can see that we have introduced this high di by dt states. And moreover, within one switching period, we are changing this arm current multiple times to control the capacitor voltages. Load current can be maintained at fairly constant. And again, as I mentioned, we have this closed loop control where we change the insertion current references and insertion times to account for errors, delays, and dead times. These are our measurement results. And as you can observe, and these come from our sensors that's embedded on the PEBB itself. And you can observe that the capacitor voltage deviation is fairly small. It's 3% for a 32.5 microfarad capacitor, which is okay, much smaller. In conclusion, we developed this switching cycle control that can reduce the PEBB capacitor and arm inductors by at least an order of magnitude, and at least an order is more on the conservative side. SCC was also extended to 4 PEBs per arm, and again developed a scalable for multiple cells per arm. We accounted for non-ideal factors like feedback measurement errors, delays, and all these things that can are detrimental to your capacitor balancing, and you developed a closed loop to counter these using arm current and duty ratio. And we verified this control for 24 kV MMC operation for DC-DC. Thank you so much for your attention. If you have any questions or comments, I'm happy to take them. Thanks.